Usually, when you look up at the night sky, you think of the moon as this great mysterious frontier.
Oh, absolutely. It's the classic unknown.
Right. But the reality of modern astronomy is that we have mapped the surface of the moon to an incredibly precise
Yeah,
degree.
down to the meter.
Exactly.
Yeah.
I mean, if you point a telescope up there or look at the satellite data, scientists can literally name every single crater, every dry valley, every jagged ridge. It is a known quantity.
Well, it's fixed in place, right. And
Uh-huh.
more importantly, it's completely visible.
Yeah.
We can just, scan it with lasers from orbit.
Hmm.
We use high-resolution photography, and we just know the topography. There's no atmospheric interference.
Right, no clouds or anything. But
Yeah.
then, and this is what's wild, you take that exact same technology and you point it back down at our own planet. You look at the Earth, and the vast majority of it is covered by this impenetrable, swirling blue curtain. We literally know more about the barren, dusty surface of a rock floating, roughly 240,000 miles away in the vacuum of space than we do about the bottom of the ocean right here on our home planet.
It's incredible. It is an absolute blind spot.
It really is.
We are quite literally flying blind when it comes to the deep ocean. I mean, it is the ultimate diagnostic challenge for planetary science right now.
So let's unpack that challenge today. For those of you listening, we are taking you on a mission to map the unknown. We're going to take a deep dive into the profound mechanics of Earth's oceans.
And it's a massive topic.
Massive. I've been poring over a huge stack of research for this. I've got encyclopedic breakdowns of biological and physical oceanography, raw marine data from NOAA, some really fascinating climate modeling from the energy company MOVE.
Yeah, that MOVE data is super interesting.
It really is. And on top of that, a provocative engineering analysis on deep sea mining from Create Digital. And the goal here isn't to just recite a list of fish species or memorize oceanic zones.
Right. Nobody wants a textbook lecture.
Exactly. The mission is to connect the systems. We need to help you understand the ocean not as just a static body of water, but as an incredibly complex, interconnected machine.
Because it is a machine. The water that covers 71% of this planet interacts with the air you breathe,
Yeah.
the climate you experience, and ultimately the immense technological dilemmas we are scaring down as we attempt this global green energy transition.
Yeah, when you look at the raw numbers, the realization hits you really fast. This planet is completely misnamed.
Well, for sure.
We call it Earth, right? Which implies a world defined by dirt and rock. We really should be calling it ocean.
The math strongly supports a rebranding, honestly. I mean, the world's oceans cover nearly 71% of the planet's surface area. We're talking about 361 million square kilometers.
It's hard to even picture.
It is. And when you factor in the depth, the volume is staggering. The oceans hold 97.5% of all the water on the planet. That is roughly 1.335 billion cubic kilometers of water.
Okay, wait. I tried to visualize 1.335 billion cubic kilometers earlier, and my brain just sort of short-circuited.
It's essentially an incomprehensible number.
Right. So I did the math. If you were to drain the ocean completely, gather all that water, and freeze it into a single solid cube,
Right.
that cube of ice would be over 680 miles wide, long, and tall.
Wow.
It would stretch from New York City all the way past Ohio and reach all the way up into the exosphere where satellites orbit. It is just an incomprehensible amount of mass.
That's a great analogy. It really puts the sheer weight of it into perspective.
But it brings up a huge question. Where did a volume of water that massive even come from?
So that is actually one of the most heavily debated questions in geology.
Right.
Yeah. But the evidence shows that water has been here practically since the Earth's violent formation. There's a geological site in Greenland called the Isua Greenstone Belt. Researchers there have found what's called pillow basalt.
Oh, wait. Pillow basalt that's the bulbous rock that only forms when lava erupts directly underwater, right?
Exactly.
The cold water instantly crunches the outer crust of the lava, forming these pillow-like shapes while the inside just keeps flowing.
You've got it. And we have confidently dated those Isio basalts to 3.8 billion years old. So we know for an absolute fact there was a standing ocean 3.8 billion years ago.
Wow, 3.8 billion.
And it pushes back even further. In the Nouveau-Guétuc Greenstone Belt in Quebec, researchers have found isotopic signatures of water in rocks that might be up to 4.28 billion years old.
And the Earth itself is only, 4.5 billion years old?
Exactly. Keep that in mind. The planet had barely formed.
So, okay, the Earth coalesces out of the solar nebula. It's this hellish, molten ball of rock. And almost immediately, geologically speaking anyway, it's covered in 1 billion cubic kilometers of water. How does that physical mechanism even work?
Well, it was an incredibly chaotic process.
Yeah.
During the very early stages of planetary formation, a significant amount of the primordial water molecules actually escaped Earth's gravity.
Because it was too small.
Right. The planet was smaller, less massive, and just didn't have the gravitational pull to hold on to lighter gases being blasted by solar winds.
Yeah.
We call that atmospheric escape.
Okay, that makes sense.
But as the planet gained mass, the interior was just churning. We had massive magma oceans covering the surface, and the intense, continuous volcanic activity drove a process called outgassing.
Outgassing?
Yeah, the volcanoes were constantly belching massive amounts of water vapor, carbon dioxide, and other gases from the Earth's mantle directly into the early atmosphere.
So the atmosphere was basically just super saturated with volcanic steam.
Completely saturated, thick, choking steam. And then you add the late heavy bombardment to the mix.
The asteroid impacts.
Right. The inner solar system was a total shooting gallery back then, and Earth was being pummeled by meteorites and comets, and many of those were carrying significant payloads of ice from the outer solar system.
Oh, so they were delivering water, too.
Exactly. So as the Earth's surface slowly cooled down below the boiling point of water, all that volcanic steam and all that extraterrestrial ice in the atmosphere finally condensed, and it started to rain.
And I'm guessing it rained for a while?
It likely rained continuously for millions of years. Just an unending global deluge filling the initial oceanic basins.
Okay, but here's the part of that timeline that totally breaks my understanding of the physics.
What's that?
If we go back 3.8 billion years to when those pillow basalts were forming in Greenland, the sun was a lot younger. And astronomical models show the young sun was much weaker. Like, it only had about 70% of its current luminosity.
Right, the faint young sun.
Yeah. So if the solar radiation hitting the Earth was 30% weaker than it is today, the planet shouldn't have been warm enough to sustain liquid oceans. I mean, the whole planet should have flash frozen into a giant snowball, right?
You've just hit perfectly on the faint young sun paradox. It literally baffled astronomers and geologists for decades.
That's the math just doesn't work out.
Exactly. If you run the basic thermodynamic math on solar radiation from 4 billion years ago, early Earth should have been a frozen wasteland. It should have been completely incapable of hosting liquid oceans, let alone early life.
So how did it stay liquid?
The solution to the paradox lies in the chemistry of that early atmosphere. It was radically different from the air you and I breathe today. It was incredibly dense and rich in greenhouse gases.
Like CO2.
Primarily massive amounts of carbon dioxide from all that volcanism, yeah. And also methane, which was likely produced by early methanogenic bacteria.
Oh, so it acted like an extreme thermal blanket.
An incredibly heavy blanket. Those greenhouse gases trapped whatever internal heat the young Earth was still generating from its formation, along with whatever weak solar radiation it was actually receiving.
And that kept it warm enough.
Right. That intense greenhouse effect created an equilibrium. It kept the planet just warm enough for the water to remain a liquid, basically preventing the oceans from becoming a solid block of ice.
So extreme global warming essentially saved the early oceans.
Paradoxically, yes.
It really highlights how the boundary between a liquid ocean and a frozen rock is entirely dependent on a super fragile atmospheric balance. And even the physical boundaries, like the coastlines we know today, are totally transient.
Well, complete.
I mean, when you look at a map today, the continent seems so fixed. But the concept of a coastline is an illusion. It's just a momentary snapshot in geological time.
It is entirely temporary. The sea level is dictated almost entirely by the Earth's climate cycles. When the planet shifts into a glacial period, massive volumes of the ocean's water are evaporated, precipitate as snow, and basically become locked up in continental ice sheets.
Right, because the snow never melts to flow back into the sea.
Exactly. During the last glacial maximum, the Laurentide ice sheet covered much of North America. And because all that water was physically trapped on land as ice, the global sea level was roughly 122 meters lower than it is today.
122 meters, that's 400 feet.
It's a massive drop.
If you lower the ocean by 400 feet, the map of the world is unrecognizable. The English Channel wouldn't even exist. It would just be a grassy valley you could walk across. You could literally walk from Alaska to Russia over the Bering Land Bridge.
You absolutely could. And, the pendulum swings the other way, too.
Right, when it gets hot.
Yeah. During periods of intense global warming, like the Pliocene epoch about 3 million years ago, there was very little ice on the poles. So the oceans were holding significantly more liquid water. Plus, you have thermal expansion water physically expanding as it warms up.
Oh, right. Warm water takes up more space.
Exactly. And that pushed sea levels up to 50 meters higher than they are today.
50 meters. That's 165 feet higher.
It changes everything.
Florida is just gone. Most of the eastern seaboard of the United States is entirely gone. Every major coastal city on the planet is under dozens of feet of water. It really forces you to look at the ocean as a dynamic, shifting volume rather than just a permanent blue background on a map.
That's a great way to frame it.
And even the current geography of that volume is extreme. For practical reasons, we divide this massive world ocean into 5 basins: the Pacific, Atlantic, Indian, Antarctic or Southern, and the Arctic.
Right.
But the Pacific is just a monster. It holds 50.1% of the total ocean volume.
It's difficult to overstate the sheer scale of the Pacific Basin. It is so vast that it creates extreme geographical anomalies, the most famous being Point Nemo.
Ew, the pole of inaccessibility. This is honestly my favorite geographical quirk on the planet.
It's a fascinating spot.
For those who don't know, Point Nemo is the exact location in the South Pacific Ocean that is the furthest away from any landmass. It is 2,688 kilometers from the nearest speck of rock,
Which is incredibly far.
which happens to be the Pitcairn Islands to the north, Easter Island to the east, and Antarctica to the south. If you are sailing a boat at Point Nemo, you are so isolated that the closest human beings to you are literally the astronauts aboard the International Space Station.
It's wild to think about.
Because they are only 400 kilometers straight up, while the nearest humans on land are over 2,600 kilometers away horizontally.
The isolation is so absolute out there that global space agencies actually use that exact region as a spacecraft cemetery.
Wait, really? A cemetery?
Yeah. When a satellite or a space station, like the old Russian Mir station, for example, is decommissioned, they calculate the atmospheric re-entry so that the debris crashes directly into the ocean around Point Nemo.
Oh, because there's nothing there to hit.
Exactly. The mathematical odds of hitting a ship, let alone a populated landmass, are practically zero.
It's just an orbital dumping ground.
Pretty much.
But if we dive beneath that remote surface, the geography on the seafloor makes our terrestrial mountains look like speed bumps. I mean, we always talk about the Andes or the Himalayas as the defining mountain ranges of Earth, but the longest continuous mountain range on the planet is completely underwater.
The mid-ocean ridge system. It spans an incredible 65,000 kilometers, basically wrapping around the globe like the stitched seams on a baseball.
65,000 kilometers.
And every single ocean basin has a mid-ocean ridge.
And the crazy part is, it isn't just a dead rock formation. It's an active factory.
That's actually the perfect way to describe it. The mid-ocean ridge marks the divergent boundaries of the Earth's tectonic plates. It's where the crust is literally being ripped apart.
By magma.
Yeah. Magma from the Earth's mantle continuously thrusts up into the freezing seawater, cooling rapidly and creating brand new oceanic crust. It is a region of immense tectonic violence. You've got constant earthquakes, volcanic eruptions, and hydrothermal vents spewing superheated, mineral-rich water into the abyss.
So you have this unimaginable volume of water sitting on top of a jagged, volcanically active, shifting crust. But, you know, a giant pool of water just sitting still isn't a machine.
No, it needs energy.
The mechanics require motion. They require physics. So to understand how this whole system turns, we have to grasp the vertical structure. The average depth of the ocean is about 3,688 meters, around 12,100 feet. But it plunges so much deeper than that.
Oh, significantly deeper. The extreme limit is the Challenger Deep, located at the southern end of the Mariana Trench. It drops to roughly 10,935 meters. That's nearly 36,000 feet.
That is just terrifying depth.
To put it in perspective, you could take Mount Everest, drop it base first into the Challenger Deep, and you would still have over a mile of dark water between the peak of the mountain and the surface of the ocean.
What's truly wild to me is that despite having fleets of satellites, GPS, and advanced orbital radar, we have only mapped about 26% of the global seafloor at high resolution. We have this massive gap in our planetary data.
The limitation there is the water itself. Water is incredibly effective at absorbing and scattering electromagnetic radiation.
So our tech just bounces off.
Exactly. The light and radar waves we use to map terrestrial landscapes from space simply cannot penetrate through thousands of meters of dense seawater. They bounce off the surface or get absorbed within the first few meters.
So how do we map it at all?
To map the seafloor, we were forced to rely on sonar. We are literally bouncing sound waves off the bottom from the hulls of ships. It's an agonizingly slow process.
It's like feeling your way around a dark room.
Right, you have to physically sail a vessel back and forth across the ocean, essentially mowing the lawn with sound pulses.
Because of that immense opaque depth, oceanographers can't just study the ocean as a single flat area. They have to slice it horizontally like a massive layer cake based on the physics of light penetration. The sources call it ocean stratification.
Yeah, and those vertical zones dictate absolutely everything about the physics and biology of the water column. The uppermost layer is the photic zone.
Meaning light.
Right. This extends from the surface down to roughly 200 meters in the clear open ocean. It is defined by the penetration of photons. It's the depth at which sunlight intensity drops to just 1% of its surface value.
And the physics of how that light penetrates actually explains why the ocean looks the way it does to us.
It does.
When sunlight, which contains the full visible spectrum of colors, hits the surface of the water, it doesn't all travel downward equally. The water molecules preferentially absorb the longer wavelengths of light first. So red light is almost entirely absorbed within the top 50 meters.
Which leads to some really fascinating visual phenomena.
Like what?
Well, if you were a deep sea diver and you cut yourself at 100 meters down, your blood doesn't look red.
Wait, really? What color is it?
It looks dark green or even pitch black.
That's horrifying.
It is. But it's just physics. There is literally no red light reaching that depth to reflect off the hemoglobin in your blood back to your eyes.
Because the water already filtered it all out.
Exactly.
So as you go deeper, the orange and yellow wavelengths are absorbed next. The shorter wavelengths, the blues and greens, have the most energy, so they penetrate the deepest, pushing down toward that 200-meter mark. And the water molecules scatter that blue light back up to the surface, which is why the open ocean appears deep blue to our eyes.
Spot on. And below that 200-meter boundary, you enter the mesopelagic zone, which is commonly referred to as the twilight zone.
So it's mostly dark.
Mostly. There's just enough residual light for organisms to see shadows and silhouettes, but not nearly enough energy to support photosynthesis.
And below that?
Below that is the pelagic zone, then the abyssopelagic, which contains the vast abyssal plains that make up the vast majority of the ocean floor. And finally, the hedopelagic zone, named after Hades.
Fitting name.
Very fitting. That zone encompasses the deep oceanic trenches. Down there, you have freezing temperatures, crushing hydrostatic pressure that can implode a submarine, and absolute unending darkness.
It is literally an alien environment. But, you know, if we bring our focus back up to the surface, the physical mechanics become incredibly visible, especially when you stand on a coastline. You see the tides.
Right.
The ocean comes in, the ocean goes out. We all learned the basic trivia in grade school that the moon causes the tides, but reading through the physics of how it does that, it's completely counterintuitive.
It really is a masterclass in orbital mechanics. The tides are driven primarily by the gravitational interaction between the Earth and the moon.
But it's not just a straight pull, right?
No, and
Yeah.
that's a really common misconception.
Yeah.
People think gravity is just a strong pull. But when you're dealing with massive planetary bodies, we have to look at the tidal force, which is the difference in gravitational pull from one side of a body to the other.
Let me wrap my head around that. Because
Oh.
you would normally think the sun controls the tides, right? Because the sun is monstrously huge and its gravity holds the entire solar system together.
Sure, mass is important. But distance is the critical variable in the tidal equation. Gravity weakens exponentially with distance.
Okay.
Because the moon is so incredibly close to the Earth compared to the sun, the gravitational pull it exerts on the side of the Earth, directly facing it, is significantly stronger than the pull it exerts on the exact opposite side of the Earth.
So it's literally stretching the planet.
It stretches the entire planet, rocks and all. But the water is fluid, so it deforms much more visibly than the rock does. The moon's gravity pulls the ocean water towards it, creating a massive bulge on the facing side.
Right, that's the high tide on the side facing the moon.
Exactly. But at the same time, the Earth and the moon are orbiting around a common center of mass. This rotation creates an inertial force, a centrifugal force, that pushes water outward.
Like when you spin a bucket of water around?
Perfect example. So on the far side of the Earth, where the moon's gravitational pull is weakest, that outward inertial force actually dominates. That creates a second identical bulge of water pointing directly away from the moon.
So you have these two permanent, massive mountains of water on opposite sides of the planet. And because the Earth is rotating on its axis once every 24 hours, the solid land masses are basically just crashing into these water bulges.
Exactly. The oceans want to remain aligned with the gravitational pull of the moon, but the rocky continents are basically plowing right through them as the Earth turns. The water is forced to continuously slosh, deflect, and dodge around the land.
And that interference by the continents is why tidal ranges vary so wildly across the globe.
That's the main reason, yes.
Because if you are sitting on a boat in the middle of the deep Pacific, far away from land, the tidal range, the difference between high and low tide might be less than a meter. You wouldn't even notice the bulge passing under you.
You just gently bob up and down over the course of the day.
But when that massive volume of water is forced into a narrow, shallow coastal area, the physics get amplified. And the prime example in the data we looked at is the Bay of Fundy in Canada.
The Bay of Fundy represents the absolute extreme upper limit of coastal tidal physics. It has this really unique funnel-like V shape and a very specific depth profile.
Which creates a bottleneck.
More than just a bottleneck. This geometry creates a natural resonance. It takes the water approximately the exact same amount of time to slosh from the mouth of the bay to the end and back again as it takes for the tidal cycle to occur.
Oh, it's like pushing a child on a swing at the exact right moment. The momentum just compounds.
Precisely. The incoming tide pushes into water that is already harmonically retreating from the last cycle, forcing the amplitude higher and higher. The tidal range in the Bay of Fundy can reach a staggering 16 meters.
16 meters.
You are looking at over 50 feet of water rising and draining away twice a day.
That's like a 5-story building of water moving in and out like clockwork.
It's an incredible amount of energy.
And the thing is, tides are predictable. You can print a tidal chart years in advance. But waves are a completely different beast. Waves are chaotic, and the mechanics detailed in the oceanography sources show how dangerous they can actually be.
Well, wind waves are generated by the transfer of energy from the atmosphere to the ocean surface via friction.
The wind just drags on the water.
Exactly. And the size of a wave in the open ocean is governed by 3 distinct variables: the wind speed, the duration the wind blows, and the fetch.
Fetch. That's a great word. What is fetch exactly?
Fetch is the uninterrupted distance over the water that the wind can blow in a single direction. In typical open ocean conditions, these variables create average wave heights of under 3 meters.
But the energy inside that wave isn't actually moving the water forward, right? Like out in the deep ocean, if you drop a buoy in the water, a wave passes by, the buoy bobs up in a circular motion and then drops back down in the exact same spot.
Right. The water itself isn't traveling horizontally. Just the energy pulse is traveling through the medium.
Until that energy pulse encounters the seafloor.
Exactly. As a wave approaches the coastline and moves into shallower water, it undergoes a physical transformation called wave shoaling.
Shoaling.
The circular orbital motion of the water molecules beneath the surface begins to physically drag against the rising bottom of the ocean.
So the friction basically hits the brakes on the bottom of the wave.
Exactly. The friction slows down the lower portion of the wave. But the upper portion, the crest, is still carrying its original kinetic energy and moving at its original speed.
It wants to keep going.
Right. So as the bottom slows down, the wavelength decreases, compressing the energy. The wave is forced to grow vertically. Eventually, the crest is moving so much faster than the trough that the entire structure becomes physically unstable. It pitches forward and breaks, dissipating its energy as surf.
Which perfectly explains coastal surfing. But I really want to dive into a deep ocean phenomenon that sounds like a total myth, but is terrifyingly real.
Oh, rogue waves.
Yes, normal waves are 3 meters. But the sources document the existence of rogue waves that can exceed 25 meters.
They are monstrous.
That's an 80-foot vertical wall of water in the middle of the ocean. How does an environment generating chaotic 3-meter waves suddenly birth an 80-foot monster? The physics term used in the literature is constructive interference.
So, rogue waves are essentially a statistical inevitability born from complex chaotic systems. Imagine the surface of the ocean during a severe weather event. You don't just have one set of waves.
Right.
You have dozens of different wave trains generated by different storms traveling in multiple directions, all with varying speeds, frequencies, and heights.
It's basically a messy washing machine of energy.
Now, most of the time, when 2 different waves intersect, they exhibit destructive interference.
Meaning they cancel each other out.
Yes. The crest of one wave aligns with the trough, the lowest point of another wave, and their energies cancel each other out, temporarily flattening the water.
Okay, that makes sense.
But occasionally, governed purely by random mathematical chance, the crests of 3, 4, or 5 different wave trains will perfectly align at the exact same spatial coordinate at the exact same milliseconds.
So their energies don't cancel, they stack.
They stack instantaneously.
Okay.
This is constructive interference. A 3-meter wave, a 5-meter wave, and a 6-meter wave synchronize their kinetic energy to violently birth a towering sheer wall of water.
That's terrifying.
It really is. The Dropner wave, which was recorded in the North Sea in 1995, was an enormous rogue wave that finally proved this phenomenon wasn't just sailor lore.
It was real data.
Actual laser data. And these waves exist for only a few fleeting moments before the wave trains pass through each other, and the energy disperses back into the chaotic noise of the ocean.
The thought of navigating a massive cargo ship, just playing the statistical lottery with an 80-foot wall of water that can form out of thin air, it is deeply unsettling.
I would want to be out there.
Me neither. But all that immense physical churn, the massive tides, the rogue waves, the churning currents, it's not just a physics demonstration. All that motion in the top few hundred meters is powering something much more profound.
The biology.
Yes, that 200-meter photic zone is the exact location of the most important biological engine on Earth.
And our understanding of that biological engine is actually shockingly recent. If we look back to the mid-19th century, around 1843, a prominent British naturalist named Edward Forbes proposed what he called the azoic hypothesis.
The azoic hypothesis.
Right. He claimed, with a very high degree of confidence, that absolutely no marine life could exist below 300 fathoms, which is roughly 550 meters.
And when you think about the Victorian understanding of biology, his logic makes total intuitive sense. I mean, if you go below 550 meters, the water is near freezing. The hydrostatic pressure is immense enough to shatter wood and crush hollow bones.
In an extreme environment.
And most importantly, it is pitch black. Without sunlight, there can be no plants. Without plants, there can be no herbivores. Without herbivores, no predators.
So how could a food web possibly exist in the dark?
It was a very logical deduction based on terrestrial ecology, but it was entirely wrong.
Completely wrong.
And the expedition that shattered the azoic hypothesis is widely considered the birth of modern oceanography. That was the HMS Challenger expedition, which sailed from 1872 to 1876 under the scientific direction of Charles Wyville Thomson.
The conditions on that ship must have been absolutely brutal.
Oh, unimaginably tough. They spent 4 years systematically sailing the globe, dropping these massive iron dredges into the abyss using miles of piano wire, and painstakingly winching it back up by steam power just to see what they could scrape off the bottom.
It was grueling, repetitive labor. But the scientific payoff was revolutionary. They didn't just pull up a few stray, dead specimens. From depths of over 5,500 meters, they pulled up a staggering abundance of bizarre, highly adapted life forms.
Things no one had ever seen before.
Never. They hauled up brittle stars, deep-sea corals, and completely unknown species of fish. The Challenger expedition proved definitively that the freezing, crushing, pitch-black ocean was alive.
But studying that life requires a very specific analytical lens. The literature draws a hard line between the fields of marine biology and biological oceanography. They are studying the exact same ocean, but from opposite ends of the telescope.
That's a good way to put it. Marine biology is predominantly a top-down science. A marine biologist might spend their entire career studying the behavioral patterns of a pod of orcas, the hunting mechanics of great white sharks, or the symbiotic relationships within a specific coral reef ecosystem.
So they look at the big stuff.
Right. It's highly focused on the macroscopic organisms and their direct interactions.
While biological oceanography is a bottom-up science.
Exactly. Biological oceanographers generally don't concern themselves with the sharks or the whales. They focus entirely on the microscopic foundation. They study the phytoplankton, the zooplankton, and the bacteria.
The invisible stuff.
Yeah. They analyze how the physical and chemical properties of the water, the varying temperature, the light attenuation, the availability of microscopic nutrients like iron and nitrate, dictate the blooming and dying of these invisible organisms.
Because that dictates everything else.
Right. Because those microscopic dynamics ultimately govern the carrying capacity of the entire marine food web above them.
The word invisible is doing a lot of heavy lifting here, because when you ask someone to picture the source of the oxygen they breathe, the human brain immediately defaults to a forest, you know?
Right, trees.
You picture the dense canopy of the Amazon, giant ferns, massive redwood trees. But the reality is that the ocean produces roughly 50% of the oxygen in Earth's biosphere. Half the oxygen entering your lungs right now originated in the ocean.
And it isn't coming from giant kelp forests or coastal seaweeds either.
No.
The overwhelming majority of that oxygen is generated out in the vast, open ocean by phytoplankton. These are free-floating, microscopic algae and photosynthetic bacteria just drifting in the currents of the photic zone.
Reading through the NOAA data, there was one specific organism that completely floored me. It's a marine cyanobacteria called Prochlorococcus.
Oh, yes. Prochlorococcus.
It is officially the smallest photosynthetic organism on the planet. You could fit millions of them in a single drop of water. And yet, because of its sheer, unimaginable abundance across the global ocean, this single, invisible species of bacteria produces up to 20% of the oxygen in our entire biosphere.
The scale is really staggering when you think about it. That single microscopic species generates more atmospheric oxygen than all the tropical rainforests on land combined.
That is just wild to me.
Its cellular machinery is incredibly efficient at capturing whatever faint blue light penetrates the water and converting dissolved carbon dioxide into biological energy and oxygen.
It's like an invisible global Amazon just drifting beneath the waves. Every fifth breath you take is a direct gift from a bacteria you will never see.
That's a beautiful thought.
But there's a catch.
There is a massive caveat to that biological engine. It is a system trapped in a very delicate zero-sum game. We say the ocean produces half the world's oxygen, which is factually true. But the ocean also turns around and consumes almost that exact same amount.
Right. Let me make sure I understand the mechanism here, because this is crucial. When billions of tons of phytoplankton and larger marine organisms die, their organic matter begins to sink.
Yes.
And as it sinks, heterotrophic bacteria begin to aggressively feast on that decaying matter.
And to metabolize that dead organic matter, those bacteria require immense amounts of oxygen. They pull dissolved oxygen directly out of the surrounding water column.
They just suck it right out of the water.
Exactly. When you average it out globally over an annual cycle, the photosynthesis occurring at the surface produces roughly the same amount of oxygen that the decomposition process consumes in the depths.
Wait, if the ocean consumes exactly what it produces, how is there any surplus? What are we breathing?
We are basically breathing a geological savings account.
A savings account.
Yeah. Over hundreds of millions of years, tiny fractions of that sinking organic matter reached the ocean floor and were buried in deep-sea sediment or subducted into the crust before the bacteria could fully break them down.
Oh, so they got trapped.
Right. Because that organic matter was geologically sealed away and didn't rot, the oxygen it originally produced at the surface was never consumed. It was left in the atmosphere as a tiny net surplus.
So a tiny bit of oxygen got banked every day for millions of years.
Exactly. Over eons, those microscopic daily deposits accumulated to build the 21% oxygen atmosphere that terrestrial animals rely on today.
So we are essentially living off the leftover savings of millions of years of interrupted oceanic decay that really highlight how fragile the balance is.
Very fragile.
And when that balance of production and decay gets thrown out of whack, the consequences are brutal. The research details a phenomenon called hypoxia, which leads to massive dead zones.
Yeah, dead zones. They occur when the natural biological cycle is hyper-accelerated, and it's almost always due to human intervention.
Like farming.
Exactly. When industrial agriculture uses massive amounts of nitrogen and phosphorus fertilizers, the excess washes off the fields, flows down the river systems like the Mississippi River, for example, and dumps directly into the coastal ocean.
And those nutrients act like a massive shot of adrenaline for the local phytoplankton.
They trigger an explosive, unnatural rate of reproduction. It creates a massive algal bloom.
Which, initially sounds like a positive thing. More algae means more photosynthesis, which should mean a massive surge of oxygen in the water, right?
In the very short term, yes, there is a surge. But phytoplankton have very short life cycles. Within days or weeks, that massive, unnatural bloom reaches the end of its life and dies all at once.
And then it sinks.
Millions of tons of dead organic material suddenly begin raining down through the water column. The decomposition bacteria go into absolute overdrive. The bacterial population explodes to consume the feast.
And they need oxygen to eat it.
Right. And in doing so, they strip the surrounding water of dissolved oxygen at a rate far faster than the ocean's surface can absorb it from the air.
They literally suffocate the water.
They create a zone of severe hypoxia. Any marine life that can swim fast enough, the fish, the sharks, they will evacuate the area. But anything that can't move quickly, the crabs, the oysters, the bottom-dwelling organisms, simply asphyxiates.
It becomes a literal dead zone.
Barren of complex life, driven entirely by a microscopic biochemical imbalance.
It is a terrifying display of how fast the biological engine can collapse. But the processes happening in that photic zone don't just dictate oxygen levels. They are deeply, inextricably linked to the chemical composition of the water.
Absolutely.
And the chemistry of the ocean is the primary mechanism that regulates the climate of the entire planet.
If we expand our view to the global climate system, humanity has a really bad habit of focusing exclusively on the atmosphere.
Because that's where the weather happens.
Right, but the atmosphere is highly reactive and lacks thermal mass. The ocean is the true global thermostat. The fundamental physics principle at play here is the specific heat capacity of water.
Meaning how hard it is to heat up.
Exactly. It takes a monumental amount of thermal energy to raise the temperature of water by even a single degree compared to air or dry land.
And the data from the UN and MOIV is just staggering on this front. The ocean has absorbed approximately 90% of the excess heat added to the global climate system since the Industrial Revolution.
90%.
If the ocean wasn't there acting as a massive thermal sponge, the atmosphere wouldn't just be a little warmer, it would be unlivable.
It is the ultimate thermal buffer. But the ocean isn't just a static sponge absorbing heat. It is an active conveyor belt moving that heat around the globe.
Like the currents.
Right. The wind-driven surface currents, like the Gulf Stream, are prime examples. The Gulf Stream acts as a massive thermal pipeline, dragging warm, solar-heated water from the tropical equator all the way up through the North Atlantic.
This is the reason Western Europe has a climate that supports massive populations, right?
Yes.
If you look at a globe, London is sitting at roughly the same northern latitude as parts of Canada that endure brutal freezing winters. But London has a relatively mild, temperate climate.
Because the Gulf Stream is continuously releasing that stored equatorial heat into the North Atlantic atmosphere, keeping Europe warm. But surface currents are really only the visible half of the climate engine.
What's the other half?
The true deep regulator is the global ocean conveyor belt. It's driven by a process known as thermohaline circulation.
Let's break down the mechanics of thermohaline circulation because it's fascinating. It's entirely driven by density. And density in the ocean is controlled by two factors, temperature and salinity.
Right. Cold water is physically denser than warm water, so it sinks. Salt water is denser than fresh water, so it also sinks.
Okay, so follow the warm, salty water of the Gulf Stream as it travels north. When it reaches the extreme northern latitudes near Greenland and the Arctic, it loses its heat to the atmosphere and cools down dramatically, becoming very dense.
Yes, and simultaneously, the surface water begins to freeze into sea ice. But here is the critical chemical trick. When seawater freezes into ice, the crystalline structure of the ice rejects the salt molecules.
It's called salt exclusion. The ice itself is mostly fresh water.
Exactly, leaving all of that rejected salt behind in the surrounding unfrozen liquid water.
Oh, so now the water in the North Atlantic isn't just freezing cold, it is super saline.
It's extremely salty, and this combination makes it incredibly dense. It becomes so heavy that millions of cubic meters of water literally plummet to the bottom of the ocean floor.
It's like an underwater waterfall.
It really is. And that creates a massive, slow-moving deep water current that creeps along the abyssal plains across the entire globe. This sinking action is the engine of the Atlantic Meridional Overturning Circulation, or AMOC.
AMOC.
Yes. It is the pump that keeps the global currents flowing.
But there's a massive vulnerability in this system, and the reports show it's deeply concerning. We are relying on this density pump to keep our climate stable, but by heating the atmosphere, we are melting the massive freshwater ice sheets on Greenland.
Which is pouring into the ocean.
Right. Millions of gallons of completely fresh water are pouring off those glaciers directly into the North Atlantic. Doesn't that fresh water fundamentally dilute the supersaline water?
It acts as a massive freshening agent. It dramatically lowers the salinity of the surface water.
And if the surface water isn't salty enough, it doesn't get dense enough, even if it's cold, and if it doesn't get dense enough, it physically cannot sink.
You have just described the nightmare scenario for climate modelers.
Stalling the conveyor belt?
The stalling of the global conveyor belt.
Yeah.
If that dense water fails to sink, it creates a hydraulic traffic jam.
Yeah.
The deep water stops moving south, which means the warm surface water of the Gulf Stream stops moving north.
Everything just backs up.
The entire AMOC weakens. If it stalls completely, the climate consequences wouldn't just be localized to Europe. It would be a chaotic, global reorganization of weather patterns, monsoon cycles, and agricultural zones.
We are leaning so heavily on the ocean's physical capacity to absorb heat, but the consequences of that heat are threatening to break the physical circulation we depend on. It's a vicious cycle.
It really is.
And heat is only half the equation. The ocean is also acting as our primary chemical buffer. It absorbs roughly 25% of all the carbon dioxide humanity emits every year. It dissolves directly from the air into the surface water.
But there is a strict chemical tax for that absorption.
Right.
When you mix carbon dioxide CO2 with water H2O, they react to form carbonic acid.
Which drives ocean acidification.
Exactly. Since 1950, the global mean surface pH of the ocean has dropped from 8.15 to roughly 8.05.
Now, a drop of 0.1 on a scale of 14 sounds completely negligible to the average person. I mean, it sounds like a rounding error. But the pH scale isn't linear.
No, not at all.
It is a logarithmic scale, much like the Richter scale used for measuring earthquake magnitude.
That is a crucial distinction. Because it's logarithmic, a 0.1 drop in pH actually equates to a roughly 30% increase in the concentration of hydrogen ions.
But
The surface waters are 30% more acidic than they were prior to the Industrial Revolution. And this isn't just about the water becoming sour. It fundamentally alters the biochemical availability of resources.
specifically, it attacks calcification. The added acidity consumes carbonate ions in the water.
Exactly. Marine organisms, from the massive coral reefs to oysters, clams, and even microscopic phytoplankton like coccolithophores, they rely on those freely available carbonate ions to build their calcium carbonate shells and skeletons.
And the acid locks them up.
As the ocean becomes more acidic, those carbonate ions become chemically locked up. It requires exponentially more biological energy for these organisms to build their shells.
That's awful.
And at extreme acidification levels, the water can actually become corrosive, slowly dissolving the shells they've already built. It's the equivalent of trying to construct a brick house while a chemical rain is actively dissolving your mortar.
And the tragedy is that we desperately need those shell-building phytoplankton to survive because they are the main drivers of the biological pump.
Yes, the biological pump.
This is the mechanism the ocean uses to actually lock away our carbon permanently, right?
It is the ocean's natural carbon sequestration technology.
Yeah.
When phytoplankton photosynthesize at the surface, they pull dissolved carbon out of the water to build their cellular structures and their shells.
Okay.
When they're eaten by zooplankton, or when they die, their carbon-rich organic matter aggregates into clumps.
I've heard this called marine snow.
Marine snow, exactly. And it slowly sinks down through the water column into the abyssopelagic zone.
Because the deep water moves so incredibly slowly, like taking centuries or even millennia to circulate back to the surface, once that marine snow hits the bottom, the carbon is effectively imprisoned.
It is a massive planetary-scale carbon sink.
And this sink operates on geological timeframes governed by chemical residence times, right?
Yes. The ocean is basically a giant chemical mixing bowl. Elements enter through river runoff and leave by sinking into the sediment. Some elements, like sodium, are chemically inert. Once salt washes into the ocean, its residence time is millions of years.
It just stays there.
But reactive elements, like the iron needed by phytoplankton, have a residence time of only a few hundred years before they are scavenged and sink to the bottom. The entire system is a precarious balancing act of inputs and outputs.
So let's take a step back and look at the whole staggering picture here. We have a 3.8 billion-year-old water machine.
Right.
It uses microscopic biology to produce half the oxygen we breathe. It uses its massive thermal capacity and deep water currents to regulate the global climate. It uses the biological pump to absorb our excess carbon dioxide.
There's a lot of heavy lifting.
But by forcing it to absorb the fallout of a century of industrialization, we are dangerously heating it, acidifying its chemistry, and threatening to shut down its circulation currents.
Which is why humanity has realized we have to stop.
Exactly. We are desperately racing toward a global green energy transition, decarbonization, massive wind farms, and hundreds of millions of electric vehicles.
We are attempting a massive pivot away from fossil fuels, but that pivot requires a foundational shift in our industrial base.
It requires materials.
Immense quantities of new technology, primarily high-capacity batteries, and advanced electrical grids.
Which brings us to the agonizing technological dilemma detailed in the engineering analysis from Create Digital. The critical minerals required to build this green, decarbonized future are sitting at the very bottom of the ocean we are trying to save.
This is the new, incredibly controversial frontier.
Deep sea mining.
To truly understand the pressure driving the push for deep-sea mining, you have to look at the severe limitations of our terrestrial supply chains.
Because we don't have enough on land.
To electrify the global transportation sector, the demand for metals like cobalt, nickel, copper, and lithium is skyrocketing exponentially.
Currently, we extract all of these minerals from land-based mines, but those supply chains are geopolitically fragile and fraught with human suffering.
They really are.
The analysis points out that roughly 70% of the world's cobalt is extracted from the Democratic Republic of Congo. 95% of the global lithium supply is controlled by just 4 countries: Australia, Chile, China, and Argentina.
And the terrestrial mining industry comes with a devastating ecological and humanitarian price tag. Expanding these terrestrial operations requires massive deforestation, often in highly biodiverse rainforests.
So we're destroying the land to save the air.
Exactly. It involved the displacement of indigenous communities, the generation of highly toxic wastewater tailings, and in some regions, documented systemic human rights abuses and child labor.
So from a geopolitical and environmental standpoint, many nations are desperate for an alternative source.
Desperate.
So the mining conglomerates and engineers looked at global maps and they looked straight down into the abyss. Specifically, they targeted a massive swath of the Pacific Ocean known as the Clarion-Clipperton Zone, or the CCZ.
CCZ.
It's a vast, dark stretch of the abyssal plain located between Mexico and Hawaii. And sitting right on top of the soft seabed mud, under thousands of meters of crushing water, are trillions of these objects called polymetallic nodules.
If you held one in your hand, it would look like a charred black potato.
Like a rock.
Yeah, but chemically, they are a miracle. They are formed over millions of years through a process of hydrogenous precipitation. Dissolved metals in the seawater slowly crystallize around a tiny nucleus, perhaps a fragment of a shell or an ancient shark tooth.
Just layer by layer.
They grow at an agonizingly slow rate of millimeters per million years. But over eons, they accumulate into dense rocks incredibly rich in cobalt, nickel, manganese, and copper.
It is estimated that the Clarion-Clipperton Zone alone contains 6 times more cobalt and 3 times more nickel than all known terrestrial reserves combined.
It is a literal treasure trove of battery metals, just resting unattached on the seafloor.
And the international regulatory machinery is already moving. The International Seabed Authority, or SS, is the UN-backed body tasked with managing the international seafloor.
Right, they govern the international waters.
They have already issued 31 exploration contracts to various nations and corporations, carving up 1.5 million square kilometers of the CCZ for potential extraction. That is an area roughly the size of Mongolia.
And commercial extraction could legally commence as early as 2026.
Because this is such an intensely debated, paradigm-shifting industry, we really need to look at this neutrally. We aren't taking a side here, but we are looking at the facts. There are incredibly compelling, logical arguments on both sides of this impending gold rush. Let's start with the proponents. What is the argument for dropping machines into the abyss?
The primary argument is a hierarchy of existential threats. Proponents argue that the single greatest threat to the ocean's survival, coral bleaching, acidification, AMOC collapse, is global warming caused by fossil fuels.
So climate change is the ultimate enemy.
Right. To defeat global warming, we absolutely must build batteries. Therefore, harvesting the nodules is a grim but necessary step to save the biosphere. They argue that vacuuming up rocks from a dark, relatively barren abyssal plain is vastly morally superior to clear-cutting the pristine rainforests of Indonesia for nickel or exploiting impoverished labor in the Congo.
It's the lesser of two evils.
That's the argument.
Furthermore, it shatters the geopolitical monopolies. It democratizes access to the green transition. And for impoverished Pacific Island nations like the Cook Islands or Nauru, who are sitting adjacent to these deposits, it is an economic lifeline.
It really is.
These are the very nations on the absolute front lines of climate change, watching their homes disappear under rising sea levels. For them, mining the seabed is a chance to simultaneously fund their survival and provide the metals needed to stop the rising tides.
Those are powerful, pragmatic arguments. However, the scientific and environmental opposition to deep-sea mining is equally intense, focusing on the permanence of the ecological devastation in an environment we barely comprehend.
Because the nodules aren't just resting on sterile concrete, right?
Exactly. They're deeply embedded in the abyssal sediment.
And the extraction technology is brutal. The proposed method involves lowering a massive robotic caterpillar-tracked vehicle miles down to the seafloor on a tether. It drives along in the absolute darkness, violently scraping up the top 10 to 15 centimeters of the seabed to harvest the nodules.
Just tearing up the mud.
It then processes them internally and pumps the slurry up to a surface support ship through miles of riser pipe.
And the catastrophic concern there is the sediment plumes. When these massive tracks grind into the seafloor, they kick up a billowing, massive cloud of extremely fine mud, the primary plume.
Like driving a truck through a dry lake bed.
Right. Then, up on the surface ship, the machinery separates the heavy nodules from the excess mud and seawater and aggressively pumps that wastewater back down into the ocean column, creating a massive secondary midwater plume.
I was trying to find a good analogy for this, and the best I could come up with is this. Imagine an ancient, cavernous room covered in incredibly fine dust. This dust has been settling, completely undisturbed by wind or currents for millions of years.
Okay, I see where you're going.
Then you drive an industrial vacuum cleaner over the carpet. The dust violently kicks up into the air. But because the particles are so microscopic and there is no airflow to disperse them, it takes centuries for that dust to settle back down to the floor.
That analogy actually holds up perfectly geologically. MIT researchers have studied the abyssal plain, and deep ocean sediment accumulates at a rate of approximately 1 millimeter per millennium.
1 single millimeter every 1,000 years.
It is an ecosystem defined by extreme stability and slow motion.
So if a mining tractor scrapes away the top 15 centimeters of mud, you are essentially erasing 150,000 years of geological and biological history in a single afternoon.
And we aren't just guessing about the recovery time. We actually have historical proof. In 1989, German scientists conducted the Discal experiment in the Peru Basin.
What was the experiment?
They dragged a plow across the seafloor to simulate the physical tracks of a mining vehicle. When marine biologists returned to survey the exact site 30 years later, the tracks looked like they had been made yesterday.
30 years later?
They were completely unhealed. The microbial life and the specialized sponges and fauna had not returned. On any human time frame, the destruction of the abyssal plain is permanent.
Not to mention the sensory shock. You are introducing floodlights and the grinding, deafening noise of heavy machinery into an environment that has known nothing but absolute silence and pitch-black darkness since the oceans formed.
The acoustic trauma alone is massive.
The bizarre organisms down there, the bioluminescent jellies, the blind scavengers, are hyper-adapted to that silence. The shock wave to the local ecosystem would be absolute.
So we are essentially left with a brutal trolley problem. Do we sacrifice the pristine, mysterious, slow-motion depths of the abyssal plain to extract the critical materials necessary to save the atmosphere and the surface biosphere? Which ecosystem do we condemn?
It's the ultimate environmental paradox, and it brings our entire journey today full circle. We started by looking at this vast, swirling blue curtain. We traced its origins back 3.8 billion years to a planet shrouded in volcanic steam.
We look at the extreme gravitational physics dragging the tides.
And the chaotic math birthing 80-foot rogue waves. We discovered that the freezing, crushing depths, a place Victorian scientists swore was barren, are actually teeming with bizarre life. We learned that an invisible bacteria provides the oxygen for our lungs, and that a deep, slow-moving current of super salty water regulates our global weather.
It's all connected.
The ocean isn't just a big bathtub. It is the complex, fragile, planetary life support machine that allows us to exist.
We rely on every single interlocking gear of that machine, from the surface tension to the abyssal plains.
But as we close out this deep dive, I want to leave you, the listener, with one final provocative thought. Something that connects the biology we discussed earlier with the looming threat of the mining industry.
It's a biological pump.
Yes. We talked at length about the biological pump, that incredibly vital mechanism where marine snow, the dead organic matter, slowly drifts down into the deep ocean to lock away our carbon for centuries.
Right, and the efficiency of that carbon sink relies entirely on that organic matter successfully reaching the deep ocean floor undisturbed.
So consider this terrifying variable. If commercial deep-sea mining gets the green light and thousands of machines start grinding up the seafloor, generating massive, billowing sediment plumes that spread for hundreds of miles through the water column, what happens when that suffocating mud interacts with the falling marine snow?
It's a huge unknown.
If that suspended sediment coats the bacteria, alters the chemical acidity of the deep water, or physically clogs the sinking organic matter, could those mining plumes inadvertently jam the biological pump?
It is a question that literally keeps oceanographers awake at night.
Hmm.
What if the very act of violently mining the ocean floor to acquire the batteries to solve climate change ends up permanently breaking the ocean's own natural climate regulation machine?
It is a haunting thought. So the next time you stand on a beach or look out the window of a plane at that vast, opaque expanse of blue, don't just see water. See the machine.
See the ancient, fragile engine working continuously to keep this rock habitable.
And appreciate that the murky, unexplored waters right here at home hold mysteries and consequences far more critical to our survival than any mapped crater on the moon.